Hello, dear Ridima. How are you?
Hi, I'm good. How are
You look
you?
wonderful, by the way.
Thank you, thank you. You look amazing as well.
Thank you very much. Thank you very much for accepting this. Thank you for your time for this participation. And we have already two participants. Hello, Adil. How are you?
Dear Maral, I'm sorry, now I cannot switch the camera, okay? Only by the voice.
Okay, no problem. Thank you very much for your perseverance here.
Hello, everyone. Good day. Good
Good
evening.
day. Good evening. Thank you for joining us.
Welcome. Thank you for you and introducing it.
So, dear Ridima, we can see your screen, by the way. There's no problem. Whenever you're ready, you may start, please.
Okay, great. Hi everyone. My name is Ridima Sir. I am an astrophysicist and an aspiring space lawyer and researcher like Miss Maral. And my prime area of work and interest is in space debris and SSA and sustainable orbital governance. I do some of my majority of my work at Space Generation Advisory Council, and I'm also part of the Chatham House CFC community as a youth leader working in policy. And I have previously written some papers and research for IF, GLEX, and ISA. So I will begin my presentation.
Thank you very much. Nice to meet you again.
Lovely meeting you as well. And so before we get into any of the complex ideas of or the physics, we need to first understand what we are talking about here today. And what we are talking about in the center of our issue in the current space generation is orbital debris. A lot of individuals call orbital debris space debris, but space debris doesn't just define orbital debris, but also naturally occurring atmospheric astronomical objects like micrometeorites, asteroids, and even meteorites. So orbital debris is more specific to our case today. And as Scopus, UN Scopus defines it, orbital debris is basically all man-made objects, including fragments, elements, and other things that have been created due to human activity in space. And they do not have any function, they're all defunct, and they can be payloads, satellites, anything really, but they basically have no use in space and they're just floating in our near-Earth orbit environment. And before we get into it, we need to sort of realize that space debris comes in different classifications of size. They come in different sizes. Their sizes all are different. So some of them here, as we have classified in our presentation, the greatest size is usually classified as being greater than 10 centimeter. And there are roughly around 40,000 pieces currently floating in space that are greater than 10 centimeter. But even this has a broad category of differences. This could be a of steel plate, or it could be an entire satellite. It could be a telescope. It could be rocket parts. It could be anything, but anything above 10 centimeters. And these are tracked and trackable by radars. We're going to get into that, but these are the most tracked objects, and these are the biggest in size. Then the middle ground of some of these sizes of these objects are between 1 to 10 centimeter, and they're approximately 1.2 plus 1.2 million plus pieces floating. And they're not exactly perfectly trackable. They're very tiny, but they're very dangerous. And I'll get into that as well. And then the final category of size is 1 millimeter to 1 centimeter, which is almost beyond 130 million plus pieces. And they're nearly invisible to naked eye and are available technologies for tracking. And they're very, very dangerous and very, very damaging. Some of this information that is publicly available that our audience here can also go and find are available through ESA space reports, NASA space safety reports, and these are the current estimates as of 2025 and 2026 roughly. Now, what does the size matter, but what does matter in space? What does it matter? What is the real parameter that we need to care about in space? And that comes down to velocity and collisional energy. Now, issue is some of these objects in the low Earth orbit and also the orbits in our near Earth orbit environment are going so fast that we cannot even comprehend those speeds here on Earth. They're really fast. For example, an average object travels at 7.8 kilometers per second. That's a Mach number of 23. What does that mean? That means 3 times faster than the speed of sound here on Earth. And we can compare it to even 10 times being a factor of 10 faster than a rifle bullet here on Earth. So what does that mean? It means that 1 centimeter of aluminum here on Earth will not harm you. I can hold it, we use it in our objects here on Earth, but it won't do anything, a 1 centimeter piece. But the same piece in space can create a massive collision, can create damage on our active payloads and satellites and even International Space Station. So imagine this going at 10 kilometers per second. That is the kinds of speeds that we're talking about. And the more the speed in LEO, we also have this equation here, which stands for kinetic energy equal to half mv squared. M standing for mass and V standing for velocity. So imagine the amount of kinetic energy these are holding. They can amount to hand grenades here on Earth. So relatively, these collision objects and speeds can go to 14 to 15 kilometers per second and even higher, depending on the kind of encounters that are happening, because objects in orbits are different sizes, differently angled, and these have different parameters. So these are going at different speeds. But just to compare, rifle bullet is 0.9 kilometers per second here on Earth. A hypersonic missile, as you can see here, is 2 kilometers per second here on Earth. And ISS and active satellites are around 7.7 kilometer per second, but debris impact and these fast moving debris, especially the tiny ones and the small ones, they can go above 14 kilometers per second. And as you can see, there's an exponential difference. And what is this called in physics? We call it hypervelocity impact. It basically means that these objects are completely vaporizing and they're fragmenting into thousands and thousands of new objects. Even the tiny piece, it's a new object in space. Now we understand the energy, but what does this syndrome happen? What is this phenomenon? What is this physical shenanigan happening in space? This is called the Kessler syndrome, Dr. Donald Kessler, who talked about this runaway fragmentation phenomena that happens in space. But what does it mean? It means that a collision can occur in space, maybe roughly 8 kilometers per second, and then it will create a hypervelocity fragmentation. It'll break into pieces. But how many pieces is it breaking into? It can be hundreds and even thousands and even more new pieces. And each of these pieces creates a new risk, a new probability of collision, a new issue of space debris impact. That means the collision rate exceeds the decay rate. What does that mean? It basically means that there's a higher chance that this piece will crash into another object in space than coming back to Earth or burning up in the atmosphere. So the issue is it ends up creating more and more and more debris, and it continues itself as a collision risk. Now, we have had some big issues, and it might sound scary, but ultimately we need to understand that these are not always big pieces. The big pieces end up in the news, and there are some of the ones, including the 2000 China anti-satellite test, which ended up creating 3,000 fragments. 2009 Iridium and Cosmos created 2,000 fragments. But these are the big ones. On a daily basis, the collisions come from the tiny, tiny pieces. And while it won't create massive explosions, it still poses a risk. So as a space sustainability researcher, we need to also bring in the awareness that, yes, something can sound very scary, but there is context. The big pieces nowadays, we do avoidance maneuver, which I'll get into, but we need to understand, as serious as this issue sounds, we cannot fear monitor, and we need to understand where does the fragment create risk. And understanding that risk specifically helps us understand our space environment more. And ESA currently, unfortunately, has given a verdict actually last year that even if we stopped all space launches today, the debris problem would still continue, even if between the collisions, even between the existing objects, even if we stop launches. So kind of the problem is there. There is a problem, but we need to look at it in a positive way as well. And that is what we're going to get into the next slide. So we need to understand that the big issues are not scattered across space. Thankfully, humanity hasn't polluted space fully, but there are areas which are more polluted by orbital debris and less polluted. So we need to understand context. And this is where orbital regimes come in. So these are the different regions in space which have different altitudes. Basically, how far are they away from Earth? So low Earth orbit is basically the main concern because this is 160 to 2000 kilometers away from Earth, above Earth, and it has a period of 90 to 127 minutes. So if you're trying to take a full round around the low Earth orbit around Earth, it would take around 90 minutes or 2 hours. And unfortunately, this orbital region is where 80% of all the debris exists. Literally all of 80% of every debris we know exists in this region. So there is the option of natural decay. And this decay can naturally, due to the atmospheric drag and the natural perturbations forces in this Earth region, can just naturally end up bringing. So this is a safe region, even if it's too crowded, it can still bring up. Also, context to understand, LEO is where most of our satellites and most of our commercial projects exist. So things like communications, media, entertainment, financial banking systems, these are all primarily located here. And any type of payload, most of them are in here. So even the International Space Station, this is here. Starlink and Earth observation, they're primarily located here. And 600 kilometers height, we can expect a lot of the satellites to naturally just fall back in a few years. And above 800 kilometers, that is where things get tricky because it can stay for centuries. But still, this is a nearby region to Earth to, still fix the issue. Then MEO is the medium region beyond LEO, which is around 2,000 to 35,786 kilometers roughly. And all of that region can be traveled across Earth in a period of 2 to 24 hours. And this is where the GPS satellites and the navigation satellites exist. And again, this is not too far from the LEO. So there is the option of natural decay, but the issue of Van Allen radiation belt, this is where a lot of electronic particles and electronics in our satellites can have a clash with each other. So a lot of the issues and debris here is like it can create electrical explosions, and which is why it can stay there forever because these are like much more harsh. And then we have GEO, which is the farthest away orbit in our consideration. And this is the most important for comm satellites and weather satellites, for things that are stationary, because it's a singular orbit. And it's also the place where a lot of the satellites from medium Earth orbit and GEO have a region where a lot of these dead satellites stay up. And unfortunately, because this is so far away from Earth, there is no atmospheric decay, which means any satellite that is stuck there after its life and function has ended, it will not come back here on Earth. It will probably stay there forever. And unfortunately, our current technologies haven't fully explored that region either. So there is no enforcement mechanism and there is no technology right now for that, but we can hope for innovation. Now, how do we track all of this? I'm talking a lot about these regions and the physics. Where is the actual technology? Where is the actual science? Where is the actual engineering and physics science coming in where all of this is actually solved or understood further? And this is where space situational awareness, or SSA, comes in. Because in our naked eye, we cannot see anything here from Earth, even stars as dots, and even now satellites as dots, but we can't individually tell much about them. We can't tell where they are. So what are these technologies that actually track these satellites, where they are, and how do we avoid a lot of these big collisions today? These dangerous Kessler syndrome creating collisions, how do we avoid them? So this is where radar comes in. Radar is the most effective technology that exists, and basically it emits radio pulses and it goes to the object, it hits it, and then the return signal comes back and its velocity is studied alongside Doppler shift, which then becomes effective for the really big objects. So all those 40,000 pieces, we can track them all with radar. It goes up and it hits the signal and it comes back, and we can tell exactly where it is. And alongside this, to understand more information on how this looks, how this situation looks, is optical telescopes. Now, this is not as direct as radar because radar is literally going and touching these debris with the signal, the radio signal, and it's actually getting the notification that, yes, this object is here, this object is there. But optical telescopes actually take visual analysis. So they take light and they see the reflected light from these materials, and then they come back here on Earth and we do past prediction analysis, and we also look into things like field of view. What is field of view? The telescopes have like a circle of how much it can see the sky. So that is the field of view of how much it can look into the sky. And we can see these satellites passing through these field of view, and then incorporating all of this, how bright does the satellite look, and also how far it is, we can detect a lot of these orbital debris. Alongside that, okay, we understand it is there. We understand, how do we know the exact location? When these systems are run, there's a thing called TLE propagation. TLE stands for two-line elements, and they basically hold all the information of the orbital elements of an individual space object. This means basically could be how far, how tall is it? What is the radius of the angle of where it is on Earth? What is the angle it's rotating in? And all of that kind of factors and parameters are kept in two-line elements. And the SGP4, or singular simple generation perturbations propagator, it integrates the physical phenomena. In space, things are not just a vacuum. There are a lot of astrophysical reactions happening. Interactions with the sun, interaction with moon, these have real effects of how satellite moves. So all of that information is also encoded in this propagator. And this also includes J2 perturbations, because the Earth is not perfectly circular. It has curves in some places. It's a bit weirdly shaped in some places. And all of that, which is called J2 perturbations, is also integrated in the SGP4 propagator. And alongside this, the final thing that confirms and allows us to track all of this is a probability of collision model by Monte Carlo, which is a mathematical technique to exactly see two objects that are very close or in the similar orbital region or in the same pathways or trajectories. And if there's a chance of colliding, there's a probability analysis done to exactly see what's the position uncertainty of it colliding. And this then goes on to be analyzed by government agencies, institutions, to create maneuvers. So if this is an old debris that is speeding this way, and this is a functional satellite, they will create an avoidance maneuver to go somewhere else. So, or it will try to slow down. It will try to avoidance maneuver somewhere else, and so that can go, and then it can follow back its regular trajectory path. And that is the thing that is mostly done in the current industry to avoid these collisions that I was talking about, these scary Kessler syndrome. And this is the active thing. All of these techniques, all of these tools that we just showed in SSA comes together to avoid creating more debris. The issue is, though, like I mentioned, these tools work best for the big size things, the things that are greater than 10 centimeter. But there are over 1.2 million objects in the 1 centimeter to 10 centimeter range that are very difficult to track. But good news, there are organizations coming up to track that as well, but it's still not very well understood. And that's why we need more companies and institutions working to be able to track those as well. And some of the work I have done as well has been working with telescopes, Python. There's a lot of computational work as well. It's not just technology in the physical engineering or physics instrumentation form. There's a lot of computing work. There's a lot of computer analysis. There's a lot of coding that you need to do to make sure all these parameters and systems that you've done work together well. So you need to work not just with the science, but also with developers and also institutions who record all of these data so that you can improve your surveys and analysis of what's happening in the sky. Alongside this, astrophysics being a very outright solution comes orbiting objects have some kind of effect on each other. And this is not perfect, but it's kind of like how Earth has an effect on Moon, Moon has an effect on Earth. These have an orbital resonance thing going on. So these are two orbiting bodies. They are moving in some pairing, and there's a gravitational perturbation. So this works naturally in astronomy anyways, and a lot of things in the universe can be explained by orbital resonance, but it can also be a solution for bringing back space debris to Earth. And this solution is primarily for low Earth orbit, and it's one of the solutions that are quite novel in the modern research areas. But it is very, very special because if considered into mission design, it can bring a lot of the LEO orbits or the low Earth orbits naturally after its end of life back on Earth. What does it mean? Basically, when gravitational perturbations affect each other very weirdly, and we understand in this region, this gravitational force will affect the most, the lunar or solar radiation pressure, or the solar or the sun will affect the gravity of this satellite the most. We can create these naturally occurring forces to make sure that we put the satellite after its life is done on an orbit which can slowly come closer back to Earth. So an orbit that goes like this, not circular. So eccentricity this is the thing called eccentricity, when an orbit is not perfectly circle. It's a weird shaped, oval shaped, and it tends to go around something. And this kind of thing grows over time. So when the gravitational perturbations continue in these very high phenomenon regions, the eccentricity can be taken advantage of, and it gets closer and closer to Earth. And then once we reach close to the atmospheric region, it will naturally fall back to Earth, and there's no propulsion needed. And this is a very, very good idea. But the issue is a lot of the governance in this situation does not take this into consideration. And also the issue is missions need to take this into consideration more seriously, because this way we can naturally stop creating more debris. So this is a very passive solution of deorbiting again, but there is a bigger constraint because the debris still exists. How do we clean that up? So this being a passive solution, we need active solutions as well. And this is the area that has been the most excitedly waiting for generations of sustainability experts and astrophysical and astrophysical experts and as well. I had to update this PPT a little because this is debris removal technology that has ever done a mission. So first, actively going and cleaning up a debris. Unfortunately, they shifted the date to 2028. This has been a recent change, but this is one of the types of going up and cleaning all these pieces of debris in space. So it goes and captures it and brings it back on Earth. This is the type. And there's a lot of things like AI being used in making sure the robot can judge which is an actual debris and what is a functional part of a satellite or something. And there are many ideas, and this is the most mission-ready type of way to remove technology. Alongside drag augmentation, which again relies on atmospheric drag. So it's slightly passive and it's cheaper than robotic capture, but it still needs a little bit of the understanding of atmosphere. And again, it would be something that only works for low Earth orbit. And then there is electrodynamic tethers, which actually is serious part of satellites that use EMF-induced forces. And this is a thing that relies on Earth's magnetic field. Earth has a lot of phenomena of lateness, gravitational interactions, and one of the other interactions is magnetic field. So Earth is in a way magnetically charged. So this type of technology takes advantage of that and transfers kinetic energy to the debris to come back on Earth rather than continue moving in space. And the final one, which is another very futuristic idea, it's using lasers to practically shoot at space debris and reduce their kinetic energy so that they can slowly, slowly come back to space. Usually it can be used for shifting them into different orbits, but it can also be used for a variety of other projects. The issue is laser sort of goes into the issue of actively harming satellites that are functional. So there's a fine line if certain countries end up using this for attacking other satellites rather than actually cleaning up debris. So all of these ideas are the more active ones to actually go up and clean the debris up. So this is very, very important. And again, one of the main themes, and there's a lot of physics and a lot of ideas in these as well, but a lot of them are unfortunately still in research development. So we need to see how it goes in the next few years. Now, we've talked a lot about the science, the technology, but how does this framework work? How does this system actually work right now? And where do we miss a lot of the issues? Where is the gap? And what is preventing us to actively just clean up space? So when we look at the supply chain of how the science flows and the engineering flows, it goes from ground radar optics, so the raw detection of actually where space is and collecting the space data, to then creating mathematical and computational models for understanding this data, and then doing analytics to exactly creating those trajectory platforms to sort of know exactly where they are, and then creating the probability risk of, who's going to collide into who. And then that's where the mitigation and policy guidelines come in. Currently, two institutions very much lead the discussion of space debris mitigation, which is IDC, which is the Interagency of Debris Committee, and it's under the UNOSA, alongside the Committee of Peaceful Uses of Outer Space, who together come together to create this really thick document of guidelines and rules, voluntary rules of what to do in a space mission or a satellite launch. And unfortunately, none of these rules are exactly legally binding or enforced. And compliance-wise, we've seen that for the 25-year rule, LEO disposal rule, which is basically any object in the low Earth orbit, if you launched it, you need to bring it back within 25 years. And around 40%, 40 to 70% people follow it because, like I mentioned, a lot of things in LEO naturally falls back. But the 5-year standard, which is actually a better idea, is 20 to 55%. So as you can see, it's lower, but even the massive number is only for the ones who have shared their data on whether they are following alongside tracking of the visibly available satellites that you can't track, because a lot of military and more confidential payloads in space are not exactly sharing data on whether they are following this rule or not. So there's a lot of mess there. And alongside, only less than 15 organizations signed the Zero Debris Charter. So as we can see, the science exists, ideas exist, but the enforcement for protecting some of this science and, the orbital region is not there. So we need to understand that while it might seem just like a technological issue, it goes beyond. Space debris doesn't just exist as trash there in space. It also creates issue because the biggest polluters of space actually end up not always having to deal with it the most because they have significant geopolitical powers as well. But the cleanup burden, even in the discourse, seems to be everyone, even when there are many countries that haven't even sent their first satellite. So before we look at it as just a technological issue to solve the problem, there is real governance and people issue. Alongside this, a lot of these slots in orbits are limited. These are still restricted altitudes. There are only a few altitudes where you can send satellites. It's very expensive to send a satellite and very difficult for every satellite to work beyond a certain distance. So, if all these satellites, especially mega constellations, just take up all these near Earth orbit regions, it'll be very difficult for new space nations to actually compete on that scale. Alongside that, light pollution and atmospheric pollution is already an issue from satellite launches, and a lot of these. Like I mentioned, you get a lot of light reflection. It actually affects our sky. The polluted sky in the night comes from light, but there is also light pollution here on Earth. There's also light pollution from space that's affecting our night sky here on Earth, and also the atmospheric pollution, which creates our skies in a lot of cities to look very weird colors. And unfortunately, we need to understand what are the acceptance on how far we can do what with space. And like I mentioned, the telescope data here on ground also gets affected. Like we want to track satellites, but we do so much other things. We explore space, we try to understand galaxies, stars, and the fundamental questions centuries of civilizations of humanity have tried answering. So losing that kind of thing just to satellites in a few decades is a very, very concerning thing. Now, I end my talk by saying just one thing, that orbit above us belongs to all of us. Even if there are debates on what the Kármán line is, where space begins, it is something that has given us all a lot of amazing things, a lot of amazing knowledge, and has advanced us as a species beyond what we could imagine. So let's also share this and fix all these issues together like it belongs for everyone. Thank you so much. That has been my talk.
Thank you very much, dear Ridima. Your presentation was really informative. I really enjoyed it, and I hope that we will have a lot of talks in the future with you regarding the space topic. It was really my pleasure to listen to you. Thank you very much.
Thank you so much for having me.
Thank you, dear. And now I'm going to do my presentation really fast. I wanted to talk about today about the space cleaners. You know, I want to start my presentation with a poem. The universe is infinite, but space has its limits. And as dear Ridima just explained, we have really a lot of space debris at the Leo orbit, for example. So the definition is really simple. The space debris is defined as all man-made objects, including fragments and elements, therefore in Earth orbit or re-entering the atmosphere that are no functional, but the more detailed explanation you already heard from dear Ridima right now. And the problem of space debris, they are really high speed. The objects are moving extremely high speeds, approximately 28,000 kilometers per hour, almost 7 times faster than a bullet, as you already heard right now from the Ridima. And the other problem is that satellites is already too expensive, and satellites placed in geostationary orbit can all cost millions of dollars and typically operate for about 7 to 10 to 15 years. And after that, they often become non-functional, but they don't disappear. They remain in orbit, for example. And the more debris we have, the higher the risk of collisions. And every collision creates even more debris. And we may face the Kessler syndrome as the result. And for example, Valentin Uvarov, director of the Space Economy and Politics Research Center, proposed that the major space powers, specifically Russia, United States, and China, should work together on a joint program to combat space debris. He emphasized something very important. This is not a problem any one country. This is the problem of all humanity, and it requires international cooperation. For example, we are already seeing some promising examples of this at 2021 Paris Peace Forum, an international initiative called Net Zero Space was launched. It's goal too ambitious but necessary to significantly reduce space debris by 2030. For example, another solution, in February 2025, companies like Astroscale and ClearSpace reached an important milestone in building debris removal system. The project, supported by United Kingdom Space Agency, is expected to be completed in 2028. So how do these technologies work? There are several proposed methods. The detailed information, dear Ridima, is explained right before me. But for example, laser system that can alter the trajectory of debris, capture satellites. One particular interesting idea comes from Russian scientists at Omsk State Technical University. They proposed a space robot cleaners. For example, the technology that can clean space cleaners, isn't it incredible from one side? And just imagine this powerful technology capable of moving satellites could also be used in dual use capacity. At this point, how can we guarantee that such technologies won't be turned into weapons or eventually violated international agreements? Or should we accept the risk as we do with many advances in our lives? And the Kessler syndrome, in a few words, is a serious risk. It's described a scenario where collisions between objects in space create a chain reaction. If this happens, we can no longer launch new satellites safely, communication system fail, GPS and weather forecasting are disrupted, for example. This wouldn't just affect space agencies, it would impact everyday life on Earth. What does this all come down? Both on Earth and in space, we are faced with a choice. We can continue to push forward without considering the consequences, or we can take responsibility for the environment we are creating beyond our planet. The question is not just technological, it's ethical. What kind of legacy do we want to leave? Will space remain a place of opportunity, exploration, and discovery, or will it become a dangerous, unusable environment shaped by our own neglect? The responsibility is ours, and the time to act is now. Thank you very much for joining.